Well, magnets have some common properties. All magnets have two poles, and that's where the force of attraction is strongest. There are no monopoles. If you break a magnet, you get two poles again. Keep breaking it, you'll continue to get two poles and cannot create a monopole. Like poles repel, unlike poles attract. So that means the north attracts south and north repels north. Magnetic field lines are the lines to which a tangent drawn at any point gives the direction of the magnetic field at that point. Another property of magnets is that if it's freely suspended, it points in the north-south direction. Now, the Earth's magnetic field has three elements. One is called the declination, the second is the inclination, and the third is the horizontal component of the Earth's magnetic field. Remember that the magnetic pole in the north is actually magnetically a south pole, and the magnetic poles actually do not coincide with the geographic poles. The line joining the two magnetic poles, the magnetic north to the magnetic south, is called the magnetic meridian, and the line joining the geographic poles is called the geographic meridian. So you have the magnetic meridian and the geographic meridian. The angle between the geographic and the magnetic meridian is called the declination. As you can see in the figure below. And its value varies anywhere between 0 to 20 degrees depending on what place you are on the Earth. And normally the Earth's magnetic field is not horizontal. It makes a certain angle with the horizontal, and this angle that the Earth's magnetic field makes with the horizontal is called the angle of dip. In the figure, theta is the angle of dip, B is the Earth's magnetic field, which is resolved into BV and BH, and we get these three formulas. Now remember that wherever there is an electric current, there is a magnetic field, and the nature of the magnetic field depends on the shape of the conductor. If it's a straight conductor, then the magnetic fields are in the form of concentric circles as shown, and it's given by the right hand palm rule, with the thumb pointing in the direction of the current and the direction of the closed fingers giving that of the magnetic field. Now if it's a circular loop, then the magnetic field is as shown here. You can see that the field is not uniform, it's strong inside the coil and weaker outside. The direction is again given by the right hand palm rule as shown in the figure. with the thumb pointing in the direction of current and the direction of the closed fingers to the tip of the fingers, showing the magnetic field. And if there's a current carrying conductor situated in a magnetic field, there will always be a force on it. That force is given by ILB sine theta. I is the current, L is the length of the conductor, B is the strength of the magnetic field, and theta is the angle between the current and the magnetic field. This force becomes maximum when theta is 90, and sine 90 is 1, so it will be F max is I times L times B. And this can be written as I L cross B. If a charged particle enters a magnetic field, a force acts on it, and this force is given by Q V cross B. Q is the charge, V is the velocity, and B is the strength of the magnetic field. Now, V cross B can be written as VB sine theta, and therefore the maximum force happens when the charged particle enters at right angles to the magnetic field. And if it enters parallel, there is no force acting on it. And once again, the direction of the force is given by the right hand rule, with the fingers pointing in the direction of the velocity of the charged particle, and then the fingers are rotated through 90 degrees to give the direction of the magnetic field, in which case the thumb gives the direction of the force. Lorentz equation actually gives the total force acting on a charged particle that enters a space that has both an electric field and a magnetic field. The first term in this case, Q, the first term is Q E gives the electric force, and the second one, Q V cross B, gives the magnetic force. And the terms are familiar. Q is the charge, E is intensity of electric field, V is the velocity, and B is the intensity of magnetic field. The units: magnetic field is measured in Tesla, velocity of course in meter per second, and strength of the electric field Newton per coulomb. Tesla can be written as 1 Newton by ampere meter from the formula F is equal to ILB, and rearranging you get B is F by I times L. So you get it as 1 Newton divided by ampere meter. Velocity selector is an arrangement where you filter out particles that have the same velocity. Here you have an electric field and magnetic field set up in the same space in such a way that the forces acting on the charged particle entering that space are equal but opposite. And that's why QE, the electric force, is equal to QV cross B, and then the charges get cancelled, and the velocity of the charged particles that pass through is given by the ratio of the electric field to the magnetic field. And this velocity selector is used in many equipment, and primarily in Bainbridge mass spectrograph, which has been used to discover a lot of new isotopes. If an electron enters a uniform magnetic field, then the force that acts on it is QVB, which is the maximum force, and this is the centripetal force given by mv squared by r. So rearranging, you get R is mv by qb, and this is the principle used in the cyclotron. And a current carrying loop set up in a magnetic field has a torque acting on it, which is given by NIAB sine theta. Mu is equal to NIA is called the magnetic dipole moment. The electron was discovered by J.J. Thomson, and this is the apparatus that was used to find the specific charge of the electron. And in this case, the maximum force EVB is the centripetal force. Rearranging, you get E by m as velocity divided by BR. And if the strength of the fields is adjusted so that the forces are equal, then E is EVB, from which you can get a formula for velocity. Substitute it back into the original formula and you get the E by m as strength of the electric field divided by the square of the magnetic field times the radius. By measuring the radius, hence the specific charge of the electron, which is E by m, can be calculated. Thank you.